Welcome to the Rani Chennamma University, Belgaum, BSc Physics 4 Sem Interference. Session 4. This session 4, it consists of thin films, conditions for maxima and minima in the case of reflected light. The learning objective of this session is to understand the thin films and to derive the condition for maxima and minima in case of reflected light of thin films. So we need some prerequisites as a phase difference and a path difference, and also the interference due to a division of amplitude and Stokes law. The path difference for a constructive interference is n lambda, and for a destructive interference the path difference equal to 2n plus 1 lambda by 2. The interference due to a division of amplitude. So in the division of amplitude, the amplitude of the incident wave originating from a common source is divided into two or more parts by reflection or transmission in thin films. The divided beams are made to reunite to give rise to the interference band. So the interference in thin films due to the division of amplitude. Stokes law. So using this Stokes law, it applies when the reflection from the denser medium or a rarer medium. So when the light wave is reflected at the surface of optically denser medium, it suffers a phase change of pi or a path difference of lambda by 2. But there is a no phase change occurs when it is reflected from the surface of the rarer medium. Interference in thin films. Thin films like oil or oil on a water, soap bubbles, or thin cracks of glass are illuminated by an external source of white light. It produces colors are uh, to be observed. This phenomena is observed and developed by Newton and Hooke. This is due to the interference phenomena due to a multiple reflections from a surface of thin transparent film. The colored phenomena can be explained by two types: the interference due to a reflection of a light and interference due to a transmission of light. The interference occurs between the reflected waves from front and a back surface of the thin films, that is due to interference of reflected wave. We'll get the bright and dark fringes. And then number 2, interference occurs between the transmitted portions of the light waves. So here we are going to study for reflected waves. Interference in thin films due to the reflected light. So consider the film PQ and RS. The thickness of the film is T and the refractive index of the film is say mu. Let a incident ray, say AB, makes an angle I with a normal drawn at the surface of separation of two media, say PQ, and it will get a partly reflects along BC and partly refracts along inside the film, say BG. So this BG, it will incident at an angle R along the normal GM, and then it will get partly get reflected along GD, and at a point D it is transmits along DE. Here the ray DE and BC are exactly parallel, but there is a path difference between them, BC and DE having the path difference BF. So as the ray it is moving from B to F, it covers the path BGD. So therefore the actual path difference equal to BG plus G, the GD, and minus to that of the path difference across the BF. So if the thin film is very thin, then the two reflected rays BC and DE lies close to each other and get superimposed and produces an interference pattern. Due to the rays BC and DE, if the film is very thin, they are very close to each other and they will get interfere, will get an interference pattern. Now let us find the path difference of reflected light. So here initially draw the perpendicular DF to BC and GM to BD. When the ray BC travels the distance BF in the air, the ray DE travels the distance BGD in the medium. Then the optical path difference is given by path difference equal to delta is equal to mu BG plus GD minus BF. This is 2 times 2 mu BG minus BF. Say this is equation 1. Then you find BF and BG, then you substitute the values in the equation 1. So to find the value of BG, so in the right angle triangle BGM, BG is equal to T divided by cos R, as cos R equal to mg by BG. So mg is the thickness of the film, that is T divided by BG. Then again in the right angle triangle BDF, we get a BF equal to BD into sin I, where BD is equal to BM, 2 times to the BM, and then this is 2 BM into sin I. So as BM equal to mg into tan R, that is mg is T into tan R. Then mu is equal to sin I by sin R. So after substituting these equation in BF, so BF we get 2 mu T sin square R divided by cos R. Then you substitute the value of BF and BF and BG in equation 1. We get the path difference. Substituting the values of BG and BF in equation 1, we get the path difference equal to delta is equal to 2 mu BG minus BF, as BG is equal to T divided by cos R, and this BF equal to 2 mu T sin square R divided by cos R. After simplification, we get delta is equal to 2 mu T cos R. This is the path difference that we get in the case of reflected light. But the true path difference is depending upon which medium it will get reflects. So as the ray is reflected from an optically denser medium at B, it suffers a phase change of pi, which is equivalent to the path difference of lambda by 2. Therefore, the true path difference is 2 mu T cos R minus lambda by 2. Say this is equation 3. Then conditions for maxima and minima in case of reflected light. Then we equate the path difference for a constructive interference condition and also for a destructive interference condition. For a constructive interference, we get the path difference equal to n lambda, where n equal to 0, 1, 2, 3 and so on. Then true path difference is 2 mu T cos R minus lambda by 2, and that is equal to n lambda. So therefore 2 mu T cos R equal to 2n plus 1 lambda by 2. So this is the condition for maxima. For a bright fringe, we get 2 mu T cos R equal to 2n plus 1 lambda by 2. Say this is equation 4. Next, condition for minima. For a dark band occurs in the destructive interference when the path difference equal to 2n plus 1 lambda by 2. So where n equal to again 0, 1, 2, 3 and so on. Therefore, the true path difference we have to equate with the 2n plus 1 lambda by 2. So as 2 mu t cos r minus lambda by 2 is the true path difference, that is equal to 2n plus 1 lambda by 2. So after simplification, we get 2 mu t cos r equal to n lambda. Say this is equation 5 and this is the condition for minima. And then, so we have seen the conditions for a maxima and minima in case of a reflected light. Let us see the problem on the basis of this one. A parallel beam of a light of wavelength lambda equal to 5890 into 10 to the power minus 10 meter is incident on a thin glass plate mu is equal to 1.5 such that the angle of refraction into the plate is 60 degree. Calculate the smallest thickness of the glass plate which will appear dark by the reflection. So here we have to use the minimum condition, condition for minima, that is 2 mu t cos r equal to n lambda, and you by substituting all we can easily calculate the thickness of the glass plate. So these are multiple choice questions for revision of whatever we have learnt. The colors exhibited by the transparent air thin film is due to, no doubt it is an interference, as the options are a diffraction, interference, polarization, aberration, but the answer is B, interference. Next, when a light travels from a faster medium to the slower medium, the refracted ray, the options, the change the phase by lambda by 2 and the change the phase by lambda by 3, change the phase by lambda by 4 and none of the above. So here the change of phase of the lambda by 3. Next, the condition for maxima of interference in thin films in case of reflected light is, maximum condition is 2 mu t cos r equal to 2n plus 1 lambda by 2. Hence the answer is C. Okay. And now condition for minima of interference in thin films in case of reflected light, that is 2 mu t cos r equal to n lambda. So the answer is B. And this is a one problem which is that I have discussed earlier. As a parallel beam of a light of the same lambda equal to 5890 angstrom is incident on a thin glass plate of a refractive index 1.5 such that the angle of refraction is 60 degree. Calculate the smallest thickness of the glass plate which will be appear dark by the reflection. So after calculating we get the answer is A, 3.9 into 10 to the power minus 7 meter. So we have studied in this session thin films and the condition of interference bands for a maxima and a minima in case of reflected light. These are the few references that you can refer. Thank you.